So let's first look at discrete time optimal controls. This is chapter 9 book. Book is in the production now. In about a month or two, it will be available. Until such time, you can use these chapters. Okay, so last week we looked at the linear quadratic regulator. Okay, if you remember theories and all that, right? It was continuous time, basically. Okay, we think about rates of change of the state variables and then figure out from the start to end as a process, control process, okay, how the state variables change and how the control signal change. And therefore, overall, what is the cost? Okay, any error that is state change from zero, right, is considered a cost. And control signal, if it is high, it's a higher cost. If it is low, it's a lower cost, like that. Then we try to optimize it and figure out what are the profile, right? Profile. Right. Now, can we do it in discrete time? That is the discussion today. So why discrete time? You can see it here, modern control systems are implemented mostly in discrete level digital. Okay. So everything has been already transferred to discrete time control practice. So hence the optimal control systems or process also needs discrete time implementation. Now I want to show you this illustration here on screen. You can see state variable. You can take this as just one other state variables or all of the states, okay, represented by x, okay. But to keep it simple, let's think x as just one state variable, okay. So it starts off here, x0 times 0, and time 1, time 2, time k, time n minus 1, time n. Capital N is the last timestamp. You can think this 1, 2, 3, 4 as maybe seconds, hours, days, whatever it is, doesn't matter. It is the sampling interval, okay. So between 0 and 1, 1 and 2 is the same constant time interval. So each timestamp, each instance, right, in discrete time, we have a control signal. You can see U0 here. This is the first control signal, U1, second control system, like that. And one step before the end of the story, we have the last control signal, that is UN minus 1. Okay, there's no UN capital N, because that is the end of the story. Whatever control signal you issue at that point, right, it's not within our window of time, right? It will have an effect beyond that point, so which is not interested for us at this point. We are not looking at that whatever profile after time n. Okay, right. So this is how any control system in discrete time evolves. Okay. Now, if you want to bring in optimization into this evolution of control signal and state variables, you have to figure out a cost function. Okay, cost function along the transition, right? Cost function along the transition 0 to capital N. So, and also we have to think about how these state variables and the control signals are linked together, because it's just one single system to which you give the control signal, and as a result of that, a state change. So therefore, they are linked together. They are not independent variables. Okay. So in discrete time linear systems, right? This is how the signals are linked together. System dynamics, right? I think everybody is familiar with this notation. Xk plus 1 equals xk axk plus b. Okay. So if you don't understand this, very simple. Say you are driving a car. Okay. So you know your position now, which is xk, your present position, right? And you know your velocity. Let's say it is u. This time it is your velocity or your speed. And v is like time, right? In seconds. So if you use this equation with your position at this moment, xk, your velocity v at this moment, times the time after maybe 5 seconds. This is your new position, xk plus 1. Very simple. Position plus time times velocity or speed is your next position. And if you think x as your velocity, right? This is your present velocity, and u is your acceleration. All right. So v is again time. So acceleration times time is again velocity. You add that to the present velocity xk. What you get is your velocity uh, after 5 seconds. So this is how state transition happens. It can be position, velocity, acceleration, whatever. Okay, so that is how you should understand this notation. So it says how state variables and control signals are linked or connected. So it can be single input, single output. It can be multi-input, multi-output. So some cases UK can be multi input, more than one control signals going in. And xk is multiple state variables. Okay, so actual output is different to this one. These are state variables. Um, Actual output can be one or many of the state variables, right? Okay. So now we get to the most common cost function, right? If you want to have an equation for a cost function, right? Uh, what is the best option? A lot of people would write like this. Okay. So what is that? Jk. K means the time index. So at any moment of time, here, maybe 1, maybe k plus 1, n minus 1. Instantaneously, at that particular moment of time, okay, what is the cost? You can write it this way, one candidate cost function. So this half xk transpose qxk. What is that? Now, for the moment, remove Q, the matrix, diagonal matrix in the middle. So it is xk transpose xk. So that is all state variables as a row multiplied by all state variables as a column. So it is element-wise multiplication. So you get x1 square plus x2 square plus x3 square. This is square sum of all of the state variables. That is the state cost actually. Okay, if your state variables are too big, which means it's a cost. If your state variables are very small, near to zero, which means you have already achieved zero state, which is the desired state or zero error. Therefore. So the magnitude of the state variables represent the state cost. Okay, so this is the first part. And then UK transpose UK. Take R out of the equation or set R equals 1. Okay. What is that? All of the control signals as a row multiplied by all of the control signals as a column. Again, the corresponding control signals multiply each other element wise. U1 square plus U2 square plus U3 square and so on. So it is the square sum of control signals. Again, this is the control cost, right? So we can consider this as cost of the system state plus control at time k. Okay. Now, why this capital Q and capital R there? It is because maybe it is not very accurate to consider all the state variables as of same cost. Maybe position has a different significance than velocity. So it can be a different significance to acceleration, like that. Okay, if you think of a moving a vehicle. So maybe you want to give higher priority for position, maybe lower priority for acceleration, like that. So this Q allows you to set these values. All right. So in my MATLAB codes I shared with you, you will see the Q matrix, diagonal matrix, and different numbers there, which means I have given different emphasis, importance to different state values. Okay. Right. So same story with the matrix R. Now, if you look at the entire sequence from time 0 to time capital N, you have to evaluate this cost and add them together. So that is equation 9.3, right? If you look at the first term, k equals 1 to n. This is k1 to n, right? State cost. So summation of all of these, okay? Plus k equals 0 to n minus 1, because control signal goes from 0 to n minus 1. I explained to you a while ago, right? We don't consider the control signal at the end of the time, okay? Because it doesn't come into our equation. It is whatever effect due to that control signal is beyond our time horizon. So therefore, when you get the cost of the control signal, you have to get it only up to n minus 1, not to n. But it starts with 0, because at the very beginning, there is a control signal. The first term here, we do not start with 0, right? But at 0, there is non-zero state. So therefore, there is a state cost at time 0. So I have written it over here. For some reason, you will understand it maybe a little later. Okay, so this is the initial state cost. And after that, k gets to 1, then 1 to n, all of the state costs are here. You start with 0 and end at n minus 1. So all of the control costs are here. Okay. Now, if you look at the summation, first one goes from 1 to n. Second summation goes 0 to n minus 1. So they have the same number of terms, but shifted by 1. Shifted by 1. Okay. So other than that, their number of terms is equal. They have the same number of terms. Now, what we do next is we want to minimize J. We want to minimize the cost, total cost. Okay, and we know how we can do that is by selecting UK, the optimal controls. Okay, from 0 to n minus 1. We have to find out this n number of control signals. Okay, so that is the problem at hand. Now we have xk over here, state, which is which depends on control signal. You saw it earlier. So we have to get rid of this xk. If you keep xk in your cost function, you won't be able to optimize it with respect to u, because xk depends on u, right? Therefore, we can find out these equations and replace xk in the equation. But before that, we will bring this 9.3 a bit further down, because you know summations can be written as matrices. Okay, or matrices can be written as summations, either way. So now we are trying to convert this summation into matrices, because in the implementation, particularly in MATLAB is designed for matrix operations, linear algebra. So we convert summations into matrices. When you do that, you can write this entire expression as this. From here to here, This is just the first summation. So you can figure that out. When k equals 1, it is xk transpose q times xk, right? So we have it here also, x1 transpose q times x1. And then the second term is x2 transpose q x2. We have it here, x2 transpose q x2. Finally, we have xn transpose q and xn. So we have that also here, xn transpose q xn. Do you see that? So the entire summation here, product and sum, is now just three matrices, the big three matrices. And if you look at the new matrix over here, it is multiplication of, right, same Q matrix along the diagonal, right? So you have n number of these elements now along the diagonal. Is a big matrix, but you can handle this as symbols, right, in your derivation. And if you look at this vector here, it is also a very big vector now, because x1 means not the first state variable, but all of the state variables at time 1. Then x2 means all of the state variables at time 2, and so on. So if it is a third order system, for example, state is 3 by 1 vector. And if you run this for 10 instances, at 10 seconds, every second you have control action. Okay, so 10 elements, and every state vector at every moment of time is 3 by 1. So this is 3 times 10, 30 by 1 long vector. So right, then the second term, similar to that, you have u0 to un minus 1, whereas x goes from 1 to n, u goes 0 to n minus 1, right? And you have uh, R matrix. Now all R matrices along the diagonal, okay? And then all of the control signals over here. So we want to find out what are the most optimal set of control signals, u0 to un minus 1. This is actually what we want to optimize, find out, okay? Right. And the final term is this one, you just write it down. Then to simplify this long, huge expression, we introduce new terms here. So this entire vector, right, all of the state vectors from 0 to n minus 1 as a very long row vector. We write it x transpose. Now this x is not the state vector, but all of the state vectors align as a, okay? And this matrix, which has the diagonal square matrices in the diagonal, okay, so is Q bar, let's say, and U transpose R bar. So that is a simple way of writing this long expression. And finally, you have one single term over here, right, without Q bar, right? It is the this X transpose thing, right, at time 0. So it is only at time 0, okay, first A. All right, so we move on. By the way, I have shared this document in the chat box, right? If it's possible, you can actually open it and refer quite easily without just sticking to what I show you over here, okay? Right. Now we have this equation 9.4. But the problem is now we want to get rid of this x over here, right? Because we can't bring x any further, because to optimize this, we want to get minimum cost, right? And with respect to u. So then x is also a variable. We can't have two variables at the same time, okay? And we know that x depends on u, so we want to find an expression to uh, substitute for x. So for that, we look at the system dynamics. This is the system dynamics, right? If you look at x1, state at time 1 is state at time 0 multiplied by a plus b using, right? This is the state transition in a discrete time. Now, if you write this for a2, it is x2, which is equal to actually ax1 plus bu1. Okay, so for time 2, it comes from time 1, ax1 plus bu1, but x1 is already here, right? Which is ax0 plus bu0. So what you do is you take this term over here, right, and put it as x1. When you do that, this a and this a multiply each other, they become a square, right? A square x0. And then this a and this b multiply each other, a times b u0, right? A times b u0. And in addition to that, you have bu1, bu1. So you get to this expression, right? If you substitute uh, your 0 time information into uh, time 2 state transition. Now, if you look at x2, right, it depends on x0 initial condition plus the two control signals given since then. Okay, it is initial condition plus the two control signals given since then. So now you are at x2. You can calculate your x2 like you are driving a vehicle, right? And you do this computation every minute, right? So time 0 is your starting point. You know your position, and then after 1 minute, you do the calculation. After 2 minutes, you do the calculation. So when you get to 2-minute point, your position can be calculated using the two velocities, right? Initial and 1 minute after that, and also your previous position, right? Where you started off. So intermediate positions are not required now. All of the intermediate positions can be represented by initial condition and control signals after initial condition. Okay, since that point. So you think about x3, then if you can follow this pattern and say that first term should be a to the 3 x0. This is like autonomous, right? If you don't give any control signals, if you just let the vehicle roll with whatever velocity it had, right? You get to a new position after 3 minutes, and this is that autonomous part. And after that, you get in addition to that, what distance is given by the control signals. So you have u0, u1, and u2, and they are multiplied with a square b, ab. You can see this pattern evolving. And finally, you can see your final position xn is given by this equation, a to the n x0. This is where you start off, long way back maybe, right? Multiplied by a to the n, this matrix. And after that, you get this, all of the velocities from beginning to one step ago, right? All of these control signals multiplied by these elements, you get your xn. Okay. Now, if you put these individual equations, right, into another big matrix equation, you can say x1, x2, x3 up to xn as your column. Remember? This is the vector we earlier developed, right? All of the states prepared in a row or a column. Then you can see all of these elements, a square, a to the 3 up to an, right? They are connected with x as a common factor. So we can write it down like this, a big, very tall column vector, a square, a3 up to an times x0. Okay? And then all of these elements, right, arranged in this format, multiplied by control signals u0, u1 up to un minus 1. Okay. So this, again, a big matrix equation, 9.6, shows you uh, all of the intermediate states, okay, of the system uh, as a function of x0, initial state, and control signals since time 0 up to that point, 20 meters. Okay. So now we can write this as vector x, right? This is not just the state vector, but all of the state vectors from time 1 to time n. Okay, without the first state. First state is over here. Let's see. And this vector, long vector, a square, a to the 3 and so on, we'll write as a bar. Okay. And this particular vector, let's write as b bar. And this vector, all of the control signals, right, prepared as a column, right, as u. Now what we gonna do is that we have an expression for x, right, which is a bar x0 plus b bar u, and write it down somewhere else. We gonna substitute this in our cost function j. Remember, this xt is all of the states, right, prepared as a column or a row. So we can replace xt over here. In fact, x, right, in two places, x transpose and x. So I think you better write it down because I'm going to advance to the next page, right, and substitute from the state dynamics for x, right? And we want to continue this 9.4 further down without x in it. That's what we're going to do now. Right. So this is what we get when you do that. So this is x transpose q bar x. Okay. Then the rest remains the same. U transpose R bar U. So these two elements are the same two elements in the cost function without any change. What we've done is we just substitute for x from this equation, right? So now in this new equation for the cost function, for the cost, there is no state vector, right? It's all about initial state x0, where you started off, and the control signals u. So even though it is not quite ready yet, we know pretty sure that this can be synthesized into a particular form so that we can find out, optimize, we can find the optimum point. Okay, what is the optimal control sequence to reduce or minimize the cost. Right. So then what we do is you multiply this uh, transpose q bar and this expression. When you do that, you have to first take a bar x0 transpose. When you do that, when you have a product and transpose, these two terms flip each other sides. Okay, so it becomes x0 transpose a bar transpose and then q bar, then a bar x0. This bar is slightly offset. I need to change that. So this bar has to come right above a. Okay, so it's a small mistake. Right. So that is first term. Other terms, when you multiply a bar x0 uh, with q bar and b bar u, and then b bar u is also over here, q bar ax0. They are same. Okay, so that is why you get these two times. The second element plus the last element is bu transpose, which means u transpose times b bar transpose. Okay, like this. Then q bar, and after that b bar q. So up to this point, it is the first term in the line above it, only the first term. And we have multiplied, expanded it three terms. And after that, you get u transpose r bar u, this term, and the other term over here. Okay, right. So even though this is kind of intimidating, it looks like it's long and difficult. It is actually not. You go into that, right? Every bit of these terms and all that is very standard thing, right? There's no complexity at all. It's just because it is too big to handle. Then what? Now you understand that uh, we can actually take out some of the terms from this. You can see that there are similar terms. Where can I see that? What about the first term here and the last term over here? Right? Aren't they similar? The first term and the last term. If you look closely, you can see they both start off with x0 transpose. They end with x0. And in the middle, it's a matrix term. In the first one, it is A transpose, A bar transpose, Q bar, A bar. And here it is just Q. But other than that, before and after, it has the same structure. So you can put them together like over here, right? You combine them together, right? And then arrange as one term like that. Okay? Just one term. So A bar transpose Q bar A bar plus Q gets into this bracket, and before that x0 transpose, after that x0. That's what we do. And also you can see uh, some u terms over here, right? This term and this term, they're showing the same pattern. They start off with u transpose, end with u, and in the middle two different matrix terms. You can have these two different matrix terms into one bracket and put u transpose up front and u at the back. So that is the second term. Then you are remaining with one term over here, that is 2x0 transpose A transpose B bar, Q bar, B bar, U. So that will remain as it is. This one. Okay. Now we can say this. We have this first term over here, which is strictly initial condition dependent. This first term entirely depend on the initial condition, right? It doesn't depend on the control system. So therefore, if you want to minimize J, the cost. Okay, there's no way for you to change it. Just unless you change the initial condition itself, which is not the objective. Yeah, we don't want to change initial conditions and see whether how it affects the optimization. Okay, the problem is you have initial state which is fixed, and then try to find out the best or optimal control sequence so that the cost from that point onwards is minimized. So therefore, you don't need to actually bring this first term forward, right? If you want to calculate the cost, that's a separate matter. But if you want to minimize the cost, okay, you don't need this term. So take that out. Keep only the terms which are affected by u, okay? Because we want to reduce the cost in those elements by selecting proper u. Therefore, first term goes out, okay? Second and third terms remain. So we now write down again to simplify this matrix term in the middle, the second term, we write it as h bar, so that the second term over here, this one, will be optically visible as half u transpose h bar u. And then the last term, we have a bar transpose q bar u bar. So let's bring f here, f bar for that. So the second term can be written as x0 transpose f bar transpose u. So here we write f bar as transpose. Okay, f bar as transpose because the matrix arrangement, it has to be like transpose. Whereas here it is just h. Now both of these terms depend on u, but how it is arranged is different. The first term u transpose h bar u, the other one just u. Now it's time to differentiate cost j with respect to u. Okay, we are not going to differentiate with respect to x0. In that case, a totally different problem. So x0, the cost depends on x0 and u. Right? When you want to minimize this one, we treat x0 as a constant, not as a variable. So therefore it goes out. So when you differentiate, this is the gradient of j cost function with respect to u. So we write that. Nabla subscript u means partial differentiation of j with respect to u as a vector. Okay. So then it becomes from the first term, right? In this arrangement, if you have a expression in this arrangement and you want to differentiate with respect to u, it becomes just h times u. And then the other one goes in this format, right? It is x0 transpose f bar transpose with respect to u. And you want to set it to 0 because that is the optimal j, optimal. Okay. Out of that, you can calculate, you can get u out as u star. This star means optimal. The optimal control sequence u star is equal to minus h bar transpose, h bar inverse f bar x. Very beautiful equations. After all these mathematical treatment, eventually you have a very concise equation, right? You can straight away calculate if you know h bar, f bar, and initial state, right? U star is the control sequence from 0 to end. So this is completely pre-computation. Even before you start the process, you know exactly what are the control signals at each and every point in time, right? So pre-planned, it's not feedback, it's pre-planned. So you need to get H bar. So H bar uh, is over here. This is H bar, right? So can you see that? H bar, right? Yeah, coming from here. And F bar, and they depend on B bar, Q bar, R bar, A bar. So then you have to go further up and find them out. It goes step by step upwards into actual A, B of the system. Okay, right. But that we can have it coded, right? Don't have to remember anything. So, all right. So let's take this system x dot t. So this is a continuous time state space model ax plus bu. Okay. Uh, Now, if you go to MATLAB and give this to MATLAB and ask it to give you the discrete state space model, right? It'll do that. Okay. For non-sampling interval. Remember the earlier example, you're driving a vehicle, you have your velocity now, you need time, right? You need time to calculate your next position. So time comes over here in this matrix, 0 and 1 over here, okay? So this is continuous time. In the discrete time, uh, what is that time difference? You have to multiply it with the velocity and add that to the position. That is your next position. So this continuous to discrete transformation should be done separately. Okay. So if you know the system dynamics, you can write down it and find it out yourself, or else you can go to MATLAB and give the sampling interval and the continuous time state space model. MATLAB will give you the discrete time state space model. For optimization, you need the cost function, right? So it is also given in this example. So what is instantaneous cost, JK? It's x1 square, x2 square. So both of the state variables, you get the squares and add to it 0.3 of the control signal square, right? So it looks like your control effort is not very expensive here. So therefore you only take 0.3 of that, but your first state variable may be position error, or second state variable may be velocity error, are important. So you keep that as is without any discount or any amplification, but control effort, you square, right? You discount. You take only 0.3 uh, portion of that. Okay. So the cost functions are context dependent, right? If you are given, you can use it, or if you want to find it out, do a reasonable assessment and find out what is the cost. Okay. Instantaneous cost, right? To solve this problem, as I said, we want to get the discrete time state space model. This is that. And this is the start or initial condition. Both of the states, they have, or they're not same, 0.3 and minus point. Okay, this is where you would set off. And your sampling interval is 0.2 seconds. Okay. Now, this is A, this is B, right? Now, you can actually find out from the first equation over here, right? Uh, Q matrix and R matrix, right? Look at this one. Arrange the cost according to the standard format, where you have X transpose QX, U transpose RU. So in that format. Okay, if you want, I can bring it in briefly. When you write down the cost, this is how we wrote the cost, right? Instantaneous cost. Q matrix and R matrix now the middle of X and U. Okay, so this example, you can look at the cost equation, this one, and arrange it into a particular format where you have X1, X2 as a transpose and then Q, then X1, X2 as a column, and then plus U transpose. Here it is single input, so just number, and then R, and then the same number again U. So of course R is 0.3, pretty obvious, right? R is 0.3, but Q is not very clear over here, right? X1 square, X2 square. When you get the squares, it is the diagonal. Off diagonal are zeros. Now you can see the first element is 1, the second element is also 1, right? And diagonal. So therefore Q is this matrix. Okay. So now you know initial point and Q and R. Also you know A and B. So if you know A, B matrices, Q, R matrices, and start point, you can implement that sequence of operations and eventually calculate. Because this H bar, F bar, they are coming from eventually A, B, Q, R. Okay. So the matrices Q bar, R bar are calculated, referring to 9.4. Go to that equation, calculate Q bar, R bar. Number of steps in this discrete sequence is 10 actually, because it's a 2 second control duration and sampling interval is 0.2 seconds. So only 10 steps. Okay. Uh, then A and B, using A and B, you can calculate A bar, B bar, A bar, Q bar, B bar, and R bar. Then you can calculate H bar, F bar. So using this MATLAB code appendix J, I will upload these codes so that you can play around with it. Appendix J. So let me go to, I can launch that for you. Appendix J. I think this is okay. So this is the code I will share with you after the lecture. And this is how it is done. The big matrix over here, right? 10 steps. So it is that big. By the way, when you run this one, don't change the steps, because then you have to change this matrix also. Okay, it's not dynamically changing. It's kind of fixed for this one. So therefore, number of steps should be maintained at 10. Uh, so let me run it. So while it is run, let me get back to this one. You can see this one. This is the control sequence already calculated, pre-computed, and we give it to the state space model and we get the result. Okay, and this U is optimal. This U is optimal, U star, right? And this is actually the result. If you go back to MATLAB, still running, uh, you get this result, right? You can see it over here. We started off with, remember, okay, now MATLAB is back and is running the code. Okay, so this is the Simulink model. This is the result, same result. Okay, so the continuous line is x1. It starts with, I think, 0.3, right, somewhere over here, uh, and dash line is x2. It starts off at 0.3, somewhere over here, and u star is the step signal with the bubbles here. This is the uh, discrete time control sequence, right? This is actually the optimal control sequence. There is no other control sequence which gives you this regulation process, because you can see both the state variables x1 and x2, they go to 0, right? Somewhere over here. They're still not there actually, right? There's a little further to go. But anyway, you know that you are actually heading in that direction, even though you are still not there. Okay. And this is the control sequence which gives you the minimum cost. Okay. Right. So this is this code, MATLAB code.m. Right. When you get this one, you can run it, and certain things you can change, like for example, initial condition. Let's see for yourself. Okay. But if you extend this time from 2 to 3 or 4 or 5, then what will happen is that uh, this matrix become that big. So you need to generate this matrix. This is A bar, this is B bar. So you have to code it in that particular size in this MATLAB code, because it's not dynamically scaling. Okay, that's the only problem. Okay, so I think it's clear to everybody. Now let's look at when we have constraints. Now in this optimization, we did not impose constraints for the control system. So any value, big or small, are possible. So we call it unconstrained optimal controls. Okay, unconstrained optimal controls. But actually, there are limits for the actuator. You cannot have infinitely big control signals. Okay, positive or negative. So there are limits. Now, how do we introduce the limits into this control signal and then recalculate a sequence within the constant? Well, again, if you go back to optimization, not necessarily controls, but optimization, this is a very standard practice. You need to have constraints, right? When you when you reduce your cost, you cannot go to the global minima, right? If there are constraints that will restrict you going to the global minimum. Okay. Suppose there is a situation, if you get a very big control action immediately at the beginning, you can control it quickly so that your control time reduces, so your energy reduces. Okay. But unfortunately, that is not possible if you have a certain limit for the control signal, so that you cannot go beyond, right? You know, some doctors do this kind of practice. When you are sick and you go see a doctor, he prescribes you a higher dose, more than what you really require. Okay, but this higher dose probably does not have any bad effects also, but it's not the general practice. General practice is you are prescribed just the right amount of dose. But this doctor gives you 20, 30% more, 50% more dose. Okay? Sometimes it works. You quickly get back to normal, right? You take the medication this morning, and by noontime, you are recovered. Okay? Suffering is reduced. Okay? But general practice is you get a small dose and it goes on for a couple of days and then you recover. Because of the time is long now, the cost is higher. That is not the optimal. Okay? That is not the optimal. So optimal control comes when the time is reduced, right? In the same time, your control signals are bigger, right? So with the constraints, unfortunately, you cannot go to that global minima because you cannot exercise these very high control signals, right? So it is not a completely new treatment now. It is just the same treatment. Only difference is now uh, we use the code frog algorithm in MATLAB. Code frog is quadratic optimization algorithm in MATLAB. Any quadratic function can be optimized in MATLAB just this way, right? You launch the command code frog, to which you have to give your optimization problem. So our optimization problem is of this nature. We have h bar, we have x bar, sorry, f bar, x zero. So these are the two terms in our optimization problem. Remember, if I pedal back and show you what we got as our last equation for optimization, just this, right? So we go to MATLAB and open the code prod, right, and give it to these numbers, right? H bar, fx0, right? In this particular format, right? It should be there. So code proc takes this format. So we don't need to give this minus and inverse and all these things, right? Because code proc is designed for that, right? It is coming from this optimization actually, okay, more than from here. So if you have this kind of optimization coming from quadratic objective function, right? You only need the two terms here, h bar and f bar x zero. So you give these two as as arguments to put frog over here, and there are so many other things you can give, linear constraints, non-linear constraints like that, and also you can give lower bounds and upper bounds for the control signal. So you're telling MATLAB, I don't want anything below the lower bound or above the upper bound. Okay, so get me the best control sequence within those lower and upper bounds. Okay, that's what you do. And if you say lower bound, this is, you have to write it down this way, lower bound, and this is the upper bound. Because in this optimization process, you have 10 control signals, right? U0, U1, U2, like that, because it is 2-second process and your sampling interval is 0.2 seconds. 2 divided by 0.2 is 10. You have 10 numbers. So for each control signal, you have to give, this is my upper bound, this is my lower bound, right? In this case, it is identical. But for whatever reason, I don't know what it is. If you have different lower and upper bounds at different uh, stages of the control sequence, you can introduce that over here. Say, for example, first half, you have these upper and lower bounds, and the second half, your upper and lower bounds are different. So you can introduce that over here, right? You just need to change numbers. All right. So then MATLAB runs and it gives you this kind of result. Okay. This is appendix K93. Let me run this one. Appendix K, this one. Yeah. Now see that on the left is actually the result you you have seen earlier, right? The same result, but I have run it for 5 seconds here, right? It was like 2 seconds earlier, right? So you can see the complete thing at this point. And this is when constraints are implemented. Now, our constraint is that you can't go beyond 1 point something. You can see it over here, upper bounds and lower bounds. The code uh, there you are. You can see this is the lower bound, this is the upper bound. Okay, so then you run the code prog. This is the optimization uh, offline. Before you start, you can do all these calculations. This is pre-computation. Okay, there you have H matrix, RB. Um, this is inequality constraints. Uh, this is equality constraints, and this is lower bound and upper bound. Okay, you don't have to worry too much about it. It's a separate discussion altogether if you want to study code prog, right? What are these inequality constraints? What are the linear equality constraints and all that? So equality constraint is that there's something equal zero. Inequality means this has to be less than or greater than zero, so, right? So anything above or below that point is accepted. But when you have equal zero, it has to be strictly agreed upon, right? You can't have any deviation from that. So all of these constraints can be included in the code program. In fact, in the book, there's a separate section for all of these things: linear, inequality, equality, constraints, everything. Okay, so you have introduced this 0.15 limit here. So initially, right, you cannot have this higher control signal, even though it is the actual optimum controls with the reduced cost. Unfortunately, you cannot exercise that. So therefore, you maintain this limit, and then after some time, you get to uh, unsaturated control signal. It goes like, okay. Now, what's happening over here is that now this is up to 5 seconds, right? Earlier, it was up to 2 seconds. If you look at the control signal, I have calculated only up to 2 seconds. After that, I let the system go, right? I let the system go and keeping the control signal zero manually, because I have written my code to calculate optimal sequence for 10 steps. But if I want to see more than that, what I can do is that, okay, set the control signal to zero from that point onwards and let the system run for 5 seconds, okay, or longer time. And if the optimal control is doing a great job, when I get to 10 steps, the control signal will have reduced to zero or closer to zero, somewhere there. So therefore, if I do repeat the zeros after that point, there's no significant transition at that point. You can see it over here, right? Even though I manually set the control signal to zero over here, even before that, it had already come down very close to zero in both cases. Okay, right. All right. Now, if you look at the discrete time optimization that we just finished, right? Um, Everything was okay except for one thing. So what is that? That one thing that is actually not very favorable for this method to be very popular or is to implement. It's because this offline nature, because all the calculations are done offline, and then you get this set of control signals, and you keep on issuing these control signals at every time step. This is not practically a very good thing to do because because of the disturbances, unmodeled dynamics, etc. in the plant is not behaving exactly the way you would have expected. Okay, by the time you calculate the optimal sequence, right? So the real state change will be slightly different from what you had in the optimization algorithm. And of course, unfortunately, this particular method doesn't have any way to do this online or real-time corrections and adjust the control gains, like control signals, to maintain the optimality and the performance. So that is why the discrete time optimal control that we just finished, right, is not very practical. So scientists and engineers were working on this problem for quite some time, and not very long ago, I think it's like in 80s, right? They came up with a solution, model predictive control. It's very recent. If you look at the entire history of control systems, the model predictive control, right? It's like some 30, 40 years old thing, somewhat recent thing, okay? So again, the highlight here is that in model predictive control, we stick to this pretty much the same set of equations, right? But we change the controls to a feedback architecture, right? From the feed forward architecture. The previous one is like feed forward, right? You don't have any real time adjustments. But here, model predictive control, it's real time feedback based adjustments, and you also maintain the optimality. Okay, all right. Now, additional information on this model predictive control was initially developed in oil industry, right? In oil industry, where a huge amount of energy is used, and they were the first people who were really, really serious into optimization, optimize the energy consumption, okay? Because they were using huge amount of energy anyway. So if you can cut down maybe 1% of energy or 0.1% of energy, that's a huge amount in dollars. So they were into optimization and how to use these optimization algorithms into real-time controls, right? That's why they were the first to develop the model predictive control, the real-time optimal controls. Okay, all right. So let me show you the overview of how this model predictive control works. You have what is called the receding horizon. Okay, you have the plant, evolving plant, right? You have the control signals coming in, state changing, and the state evolve, right, over time. Now here, we don't take the entire control sequence from zero to final, right? We take a part of that, right? Now here you can see this rectangular windows, right? Rectangles actually with say if you take the first one, 1, 2, 3, 4 steps into the future. So we see only 4 steps into the future in this particular case, and then do the what sort of optimization you want,
and calculate the control sequence. You can see it over here, U0, U1, U2, U3, U4. Right? You calculate all of these things. And you can issue these 4 control signals, or maybe 3 of them, or maybe 2 of them, or maybe just one of them. And then, right, when you step forward into the next moment, 1, you see another 4 steps into the future. Okay? Then it is the next rectangle over here. Same 4 steps, but shifted forward by 1. So now you plan the discrete optimal controls for the next 4 steps. You get yet another optimal control sequence. So out of that, you can execute maybe 1 or 2 or 3 or all 4 of them, right? Let's say here in this illustration, we issue only 1, the first control signal in the optimal sequence, and then we move forward again. So at each step, you calculate optimal control sequence for n number of or k number of steps into the future, and out of that you issue only 1 or 2 fewer number of control signals, not too many, because you know things are actually not evolving the way you predict. So therefore every step there is an error. So if you let the system to move on without correcting for far too long, errors would be very big, and you lose your performance and optimization also. So not to lose the grip on the control on the plant, right? We do not keep implementing the control signals from the optimal sequence, but we only implement 1 or 2, right? And then reassess, recalculate new optimal control sequence. So this way, it becomes feedback in real time. Okay. Now, this 4-step window is what is called the prediction horizon. And the number of steps that you actually implement your controls is the control horizon. So in this particular case, the window size is 4, that is the prediction horizon. And you only issue 1 command of that sequence before you reiterate the whole thing. Therefore, your control horizon is just 1. Okay, this is 4-1 arrangement. 4 is the prediction horizon, 1 is the control horizon. First, we look at the model predictive regulator, right? All this long, we are working on regulators where we want all the states to go to 0, right? From wherever you start off, right? Go to 0 as quickly as possible with minimum energy, right? And remember this equation, this is what we have got earlier, 10.1. Okay, so this assures you the optimal or minimum energy, right? With or without constraints. If you have constraints, you can put that in, you know how to do that. Or if there are no constraints, it is unconstrained optimization, right? So we have that. Now we introduce this equation. What is this equation? Now, when you have the control sequence calculated over here, right, it has n number of elements in U star, n number of control signals, right? Now, in our illustration earlier, right, you saw that it's 4-step prediction horizon and 1-step control horizon. We only take the first one. So if you stick to that one here also, you need to do this adjustment. U star 1k, that is the first element of U star. How we get that first element extracted or picked up from this one is by this matrix operation. So you have 1 0 0 0 for the rest times the optimal control sequence, right? This way you can immediately pick up uh, the uh, the first element in this sequence. So eventually you can form it into this format. Minus is there, and then k times xk, right? See, this is a very beautiful thing when we have seen this kind of things earlier also, particularly when we were dealing with state feedback. So what is state feedback? It is a frontline feedback control design uh, 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 criterion where you get all the states fed back through gains. This is exactly that. This is state feedback control. Okay. So even though you have come from a very different route, eventually, if you put that into, if you put the optimization into model predictive control with control horizon 1, it becomes standard state feedback control. Okay. Now, this is state feedback, very similar to state feedback, but this is optimal. This is optimal. Now, the control algorithm that we discussed earlier for discrete optimal control uh, is written over here. You start off with A, B, Q, R, N, and NP. NP is the prediction horizon, okay, and N is the control horizon. This is prediction horizon, control horizon. Then you calculate Q bar, R bar, A bar, B bar, right? Then H bar, F bar, and initial condition is given. Then you do this from 0 to n minus np minus 1 because the prediction horizon is of a certain length. So if you know your final point, in fact, this n is the total length, okay? You have to reduce from it np minus 1 steps. So this is where you stop your model predictive controller, right? You can't bring it to the very end because model predictive controller has its own width, okay? So you can go as far as the width fits into the endpoint of the timeline. So which is n minus np minus 1. So then each step you calculate the optimal controls, right? With xk. Xk is the not 0 now. Xk is the present state, right? Initially it is x0, but now it is xk. So this is the difference now compared with what we had earlier. Earlier it was x0, remember? Everything is from 0 because we calculate the whole thing, we compute, actually pre-compute the whole control sequence. Right? So we use x0, but now it is different. We get xk, what is the present state, and from that point onwards, we calculate the optimal controls. Okay? Each step we do that. And then using this one, we update the state. This is the new state. But if you actually work with the real system, this equation is actually the real system. You read the sensor and get the states fed back to the process, right? Because here we don't have a real system, right? To which we send the controls and get the states through the sensors. We have this mathematical equation over here, okay, to update the state. All right. So that's all about model predictive control, right? It's not a very big difference, but it's basically the discrete time optimal controls reshaped into feedback control. Okay, so something similar to this we have seen earlier in the Kalman case also. The standard Kalman filter was very comprehensive, mathematically very rigorous, but then it has a little problem, right? Because you can use it for only linear systems, whereas most of the systems out there are nonlinear. So with a little tweak, you design the extended Kalman filter, right? Which is much more useful than the standard Kalman filter. Here also, the discrete time optimal control took a lot of time and effort to develop, but after that, because so after all these things, it had a very limited use because it is offline. Then with a little tweak in the process, we convert into what is called model predictive control, which has a very wide range of applications, right? But the effort put in this conversion is very minimal, right? Somebody just need to think of it, how to bring this discrete time optimal control into real time feedback optimal control. With a little glitch, you produce something very, very seriously useful. Okay. And in engineering, right, there's always constraints. So therefore, make sure you, when you do anything, you look at the constraints and respect the constraints and do whatever you want to do, optimize the systems well within the constraints. So if you want to take the constraints in, it's very easy. Well, within the model predictive controller, you use the code prog or any other optimization algorithm where you can introduce the control limits, UB, LB. UB means upper bound, LB means lower bound. Then this optimization algorithm will take care of the constraints, right? If it calculate something and eventually get something bigger than upper bound or lower than lower bound, it will recalculate it to the limits. Okay, right. So now we have another exercise. I think it's Appendix L 10.2.3. So let me launch that one. Appendix L, this one. All right. So you can see much of the code is the same, right? So this is the beauty. When I wrote the code, right, with some effort in the first case, and get into the second, third, fourth cases is little effort but big benefit. Okay. So that's how everything works in the world, right? First thing is like you need a lot of effort because all of the constructions you have to do, right? Even to get to the first step. But after that, it's rewarding. Um, right. So let me run this one. So while it is running, let me get back to the exercise. Develop the finite time optimal regulator in exercise 9.3, the previous one, into a model predictive regulator considering unbound controls. Introduce control bounds and implement the model predictive regulator using hot block optimization in MATLAB. So there are two things here. One is convert the previous discrete time uh, offline, pre-computation, right, of optimal controls and convert into feedback, right? And then introduce the constraints. So what are the constraints? Minus 0.2 and plus 0.15 for the control limits. Uh, so when you do that, this is what we get. It's very similar to the previous case, but if you look at look hard, maybe this is actually feedback control. Okay. So it is not actually 0 after 2, it is going like that because uh, this works for a smaller window, right? Earlier we had 2-second control, sorry, 2-second duration for the entire process, remember? Then using 0.2 as sampling interval. we calculated 10 steps. So we took the entire 10 steps, start to end, and did the optimization and computed the control signals. One shot, okay, then implement. Then you saw in the result I showed you earlier that after 2 seconds, there's nothing, right? Either we can stop the simulation there and visualize what happened, or let the system run for additional few seconds, for which we don't have any control signal compute. So I kept the control signal beyond 2 seconds, all zeros, right? I showed you the result. But here, there's no such problem because my control horizon is 1 and my prediction horizon can be 4, 5, whatever it is, a smaller window. So then I can push it further into the edge of the control. So I can actually go for 5 seconds, okay? And maybe at this point, I have to stop my optimization because at this point, from on that point onwards, it is the prediction horizon. When the prediction horizon hits the time, right, I cannot move it any further forward, right? So after that, I have to keep the control signals 0. Now see the graphs, and this is feedback control. It's beautiful. And earlier, last week, I showed you a comparison between PID and linear quadratic regulator. We don't have to do it again here because if the linear quadratic regulator is better than PID in terms of energy optimization, there's no question about this result here. This will have similar result. Okay, right. Now we get to the last part of the discussion, model predictive tracking control. So this is very interesting. Um, I think I have explained to you there are two basic control problems. One is the regulator problem, the other one is the tracking control, right? In case of regulators, the reference is actually 0. All of the states at 0. Okay, so it's like stabilization. And if you have a disturbance, um, um, like sending the states away from 0, up or down, right? The controller immediately jumps in and control these state variables back to 0, right? Most of the results I have shown you are of this nature because they are all regulators. And in some systems, I showed you how you can use the regulator as a tracker also. There, we deceive particularly in the linear quadratic regulator. We took the first state signal, which is gradually driven to 0 by the linear quadratic regulator, and we input a negative step there, say -1, for example. Then the linear quadratic regulator thinks that it is at -1 now, so it pushes the signal to +1 actually. When you have +1 and -1 cancel out, it feeds back to linear quadratic regulator a 0. Then linear quadratic regulator thinks everything is fine because the state is now at 0. But in fact, state has already been driven to 1, right, without the knowledge uh, by the linear quadratic regulator. So this little technique that we use in linear quadratic regulator allows us to use the regulator as a tracking controller also, right? But it is not designed as a tracking controller, okay? Even though you can use it uh, with some constraints as a tracker. But here, we are designing a model predictive controller as a tracking controller from the design itself, okay? Now, uh, watch the process. Now, if you read the text here, unlike in regular design, tracking control does not target the 0 state, at the end. Okay, so tracking controllers are not like that, right? Not like regulators. Tracking controllers do not expect zero, right, as the target. They expect some reference value as the target. Uh, so this is the expectation at the end of uh, uh, predicted horizon or prediction horizon. Therefore, sustainable non-zero control signal is required at the end state. So if the end state is not zero, we have to keep giving some energy for the plant to keep the states at that state. Okay, because we assume that if the state is at zero, then you don't have to give energy. Okay, practically it might be different to that, but theoretically speaking, we can say so. If the states are at zero, no energy is required any further. All right. So now when you do that, you have this problem of in the optimization process, right? You cannot strictly apply the cost function and differentiation with respect to the control signal and set it to zero. That process is not readily designed for tracking problems where the end state is not zero, right? But you know, mathematics is very, very beautiful, right? It is very flexible. It can adapt to any situation, right? The regulator, tracker, no problem. So what we do here is we redefine our control signal, right? We don't say, okay, we have big problem here. We adjust to the situation. So you have seen, if you look at all of these transformations, everything, right? They were developed to settle this kind of problems in the past, okay? Rather than saying, no, we can't do anything. So mathematics allows you always to find a problem, right, within itself. So now what we do is we define the control signal in a different way. UK, the control signal at time k, is uk minus 1, the previous control signal, plus delta uk, delta uk. So this is a redefinition, redefining the control signal this way allows you to separate the control signal into two parts. What was there and what is being added on top of that is delta. So when you use this as a tracker, right, you maintain your k minus 1, but add on top of that delta amount, add or subtract. So when the system reaches the reference value, delta k goes to 0. Delta k goes to 0, but control signal doesn't go to 0. Control signal will keep at the previous level, uk minus 1. So this optimization is now not based on uk minus 1, but based on delta uk. All of the delta UKs, right, are the subject matter right now in optimization. What is the best sequence of delta UK from start to end, right, to optimize? So optimization is now with respect to the differential control signal. So that way we solve the problem. Now, this is the earlier result. Now, the minimization, right, the cost minimization is applied to the incremental component, delta UK, as I said, right? Because in any minimization problem, uh, you need to have this subject variable goes to 0 towards the end is a requirement. And also in this optimization, uh, what we do is we get the objective function. Here it's a cost function. Differentiate with respect to u, and in this case delta u, and set that to 0. assuming that it is a minima, right? Because we did not check this, whether it is actual minima or maximum. Because you can have the first derivative 0 for a minima or maximum in both cases. So just because you set it to 0 doesn't mean that it's a minima or maximum, right? But in this particular case, if you look at the objective function, it's a quadratic function. It's a quadratic function, which means squares. So squares cannot be negative. Squares are positive, right? Higher the squares, higher the cost. Lower the squares, lower the cost. So therefore, when you differentiate and set it to 0, there's no need of any proof because you go to minimum. Okay, that is why quadratic functions are very popular choice in objective in cost functions. Okay, when you differentiate and set it to 0, it uh, is actually a minimum that you have. Okay, right. So now we write down the state equation xk plus 1, which is equal to axk plus buk into this format, because uk is now separated into uh, elements. One is k minus 1, the other one is delta u. So you split the control signal into two. All right. So now you can arrange this state space model to this format where you have xk and uk minus 1 both as state variables and control variable as delta uk, right? So it's a new system has been transferred to a new system, because you cannot have uk minus 1 as part of your control signal. You cannot. You have to send it somewhere else. Okay, uk minus 1 is part of the control signal, but now you are sending it as part of the state variables. You have xk and uk minus 1. Okay, arrange it in this way. Now delta uk is the control signal. Okay, right. If you think of actual system like this, the control signal you have given earlier is actually uk minus 1 is part of the state now. And whatever additional amount on top of that is actually the control signal, the adjustment. Okay, right. Now what you do is you combine 10.3 and 10.4. 10.3 is this one, right? And 10.4 is this one, right? You can form this nice state space model where you have two states now, xk plus 1, uh, which is a, b, this vector xk uk minus 1 plus b delta uk, and this equation uk equals uk minus 1 plus delta uk, going along with xk plus 1 uk is equal to uk minus 1 plus delta uk. So both of these equations are now uh, combined together into the transferred state space model. We can briefly write it in this format. X tilde k plus 1 is equal to a tilde uh, x tilde k plus b tilde delta u k. It's the same plant, but a different state space model. Okay. Now, and in the text, I have written down the sizes of these matrices. But here I'm not going to discuss that because it can distract your thinking. But I strongly recommend you, when you get the text, when you read it, pay some attention to the sizes of the matrices. Okay, for example, A tilde is n plus m by n plus m matrix. Okay, why is it so? Figure it out. It's the dimensions. Okay, you can draw the matrices and on a sketch paper and write down the dimension on the right lower corner, right? And do the process yourself. You can see when the matrices multiply, how the dimensions change and all that, right? This is very, very important. I remember when I was studying these things, right? I did that the same thing because I wanted to know the sizes of the matrices, how many rows and how many columns and all that, right? How it goes on through the process. So it is a really entertaining experience if you do it that way. Okay. So I've written down here all these numbers, but I don't want to take time explaining it here. So I want to show you the process, overall process. Then the output yk is c x tilde k. Uh, uh, C comes from uh, the original state space model, and now we have additional element uk. We are not taking that as a measurement, right? Because it's only for this formulation that we use it, but actual output is still xk. Okay, so therefore it is c0 x tilde k, which means we are taking the first part of x tilde k as our the first part is of course this one. Second part is this one. We are not taking that as an output. Okay. So this 10.5 is only for this optimization process. Okay. It's just for mathematical play out. When it comes to real plant output, it is still same xk. This one. Okay. Right. Now here you can see is a P by n plus m matrix. All right. So P is number of measurements. N is the number of states in the original plant. M is the number of inputs to the plant. Okay. So inputs, states, and measurements. Now we can think about an error. So what is the error of the plant? Yk is actually what we expect towards the end. You can say that. Okay. So um, the output of the plant rather. Rk is the expectation, the reference value. So at any point during the control sequence, right, the difference between R and Y is the error. Okay, so you can define error like that. But Y is C tilde X tilde K, you can bring it over here to 10.7 equation. Now you can see how uh, the tracking model predictive tracking controller works uh, at any given time t, right? We have the prediction horizon of NP steps. You can see the rectangle over here. This is the prediction horizon. And then you do the optimization for the transferred system, right? So it is x tilde 0, x tilde 1, x tilde 2, up to x tilde n. All right. And then you have for each of these states y0 here, y1, y2, y3, and so on. And you have the references R1, R2 up to Rn, and you have errors E0, E1, E2 up to EP, and you have delta U0, delta U1, delta U2, and so on. All of the incremental control signals. Okay, uh, you can see over here some of the variables from the original state space and some of the variables from the transfer state space. Okay, and then you actually implement once you calculate the optimal delta u is equals the only the first element. In my MATLAB codes, it's only the first element, right? One can like implement first two, I know first three, as I said to you, but it's not a good idea to go further forward because then you are actually aligning with the offline computation, right? We don't want to go in that way. So now what we do is we write down the objective function um, for this one. Uh, I think you can understand it right now. With your previous experience, you have seen these things before without referring to any other equation. The first part here is the error at final point, at this point, okay, within the prediction horizon. At the end, what is the error? NP transpose Q NP E NP, right? Any error at the end of the prediction horizon, right, is a cost. And then from K1 to NP minus 1 towards the end, the running cost, right? All the errors in the process up to that point, and all the delta U control signals, right? Delta U0 to delta U NP minus 1, this point, one step before. Okay, this is the same thing that we did earlier. But now we redefine the objective function in terms of error and the differential control signal. So therefore, you can expect some sort of reduction here in the differential control and also in the error combined. So this is what we call optimality. All right. Next, what we do is we replace E, error, using this expression, because you know error is reference minus output. So this is reference, this is output, and it is transposed, and then this one error uh, at end point at the horizon is again this one, right? So up to this point, this whole thing is just the first term over here, okay? Plus you have the second term now, half k equals 1 to np minus 1, all running errors in the process from 0 to that point, okay? This is np, the last step, end of the horizon. But the summation goes only up to np minus 1, one step before that, okay? Uh, but it has the same error, right? Rk minus C tilde X tilde K, right? Same as here. And then this is the control cost. So then what do we do? So we are expanding this equation now. So you have R NP, C tilde, X tilde NP, whole thing transpose. You can break this into two terms and you write it like that. You have R NP, the reference value, right? Also here, right? It's just the expansion of the first term, right? This term you can see when you expand, right? You get to this equation. Only the first one. You have three terms: first, second, and third terms. And first and the last terms are with half, whereas the second term without half, because it is two terms together, identical terms. So it is two halves means one. Right. So take some time at home to digest all of these things. But as I said earlier, this is just the sheer length. There's no complexity at all, right? I can take you one by one and explain you everything, right? Taking time, but it's quite unnecessary. It's pretty obvious if you look at any one of these things, R and P, right? Transpose Q and P times Rn. So that's over here. Simple as that. It's like x plus y times x minus y. Sorry, x plus y plus x plus y, something like that. Same, right? So then second term can be written like that. Uh, this one rk minus c tilde x tilde k transpose this one. Same way, right? You now write one, two, three terms, then second one with number two in front because it is two identical terms, you add them together. And finally, K0 to NP minus 1 is control sequence. There you can see the first and fourth terms solely depend on the reference trajectory. First and fourth terms, look at that one. The first term and, first term, second term, third term, and fourth term, right? So this one and this one, these two terms, they are constant because that is the RK reference value. Here we don't think that the reference is changing. It's a fixed reference, right? And optimal control is trying to reach that point. So therefore, these two terms are constant. You can take out of the equation. Okay, you can't optimize it any further. It's a cost, uh, the permanent item in the cost, right? There's no point of trying to reduce it because it's there as a constant. So they both go out. Um, then you can combine the second and fifth terms. Look at that. Second term, which is this one, and the fifth term, 3, 4, 5, fifth term, right? You can combine these two together. How? And the second term over here, of course, multiplied with this half, the 2 goes away. This is RK transpose Q, C tilde, X tilde K, goes from K1 to NP minus 1, right? So it stops one step before the end point. And this one is the term, same term at the end point. So you can combine these two together and say the summation k from 1 to np. Got that point? Right? So likewise, you can combine some of the terms here. And also third and sixth terms. Look at that. Third term, 1, 2, 3, which is this one. And the sixth term, 4, 5, 6. These two terms are also same. You can see xk, x tilde k, transpose, c transpose q, c bar, sorry, c tilde, x tilde k, right? And here it is the same thing at time np, endpoint. So this goes from k1 to np minus 1, one step before the endpoint, and this is the endpoint. So you can combine the two together and say summation k from 1 to np. So likewise, you can combine all these things into this format. Eventually, it becomes like this. Half x tilde transpose q double bar x tilde minus r transpose t double bar x tilde plus half delta u transpose r double bar delta u, right? So there are these new matrices q double bar, t double bar, r double bar, right? Are like that. You can see over here, right? So So here we get two summations, right? Two summations, these two terms and these two terms separately from k equals 1 to np, right? And then the third term here. The first summation is associated with this matrix half x tilde transpose x tilde, right? So that is uh, from this one, x transpose x, x transpose x, right? Then entire expression here, C tilde transpose Q and C tilde. This is the matrix, right? That is over here. Remember this one, C tilde transpose Q C transpose, right? From 1 to n, 1 to n. All these elements, right? They align at the main diagonal. This is the summation elements, okay? From the summation k from 1 to np, k from 1 to np. And the other summation is this one and this one. So it has r and x on either side, r and x. So I take you there, r and x. See that? And in between the matrix. What is that matrix? Q C tilde is the matrix. Q C tilde along the diagonal from K1 to N. This is the last term anyway. So which is this one. Of course, there's nothing to mention. It's delta U transpose and U on either side and the middle R. Right? Okay. So the dimensions of the matrices are also given here. Now we have the same problem here, what we had earlier. That is, the cost cannot be minimized as long as you have x tilde here. X tilde is the new state of the transferred system, and it depends on delta u. So you can't have two variables here in the optimization. In that case, it's a different optimization, right? You have to get the partial derivatives and set them both equal to 0, right? Cost um, uh, partially differentiate with respect to x tilde has to be 0, and in the same time the cost partial differentiate with respect to u has to be 0 as well. That's not what we want here, because we know x tilde is a function of delta u, right, as we did earlier, and everything eventually would be function of delta u, and then we use the first order necessary condition for optimality, that is the first differentiation equals 0, and find out u, right? So therefore, we have to bring in this relationship between x tilde and delta u. That is the state space model of the transferred system, right? So what is that? I can show you the state space model we derived, which is this one, right? Which is this one. X tilde k plus 1 is equal to a tilde xk plus b tilde delta u. If you have this kind of state space model, you can write it down repeatedly for k equals 0 to 1, 1 to 2, 2 to 3, 3 to 4, like that. The same way we did earlier. And you can generate these equations. X tilde 1 is equal to a tilde x tilde 0 plus b tilde delta u 0. That is the first equation. The second equation is x tilde 2 at time 2, what is the value of the state vector? Well, it is a tilde square x tilde 0, right? From the 0 initial condition, 2 steps, plus a tilde b tilde delta u 0, the first control signal, plus b tilde delta u1, the second control signal. So this pattern continues. Eventually, we get all of the states aligned from 1 to n, right, as x tilde without any bracket, right, is x tilde. Uh, then a double bar, this whole thing is written as a double bar. X tilde 0 is when I have bracket and 0, which means in that particular time instance. Whereas this x is all of the state vectors from 1 to n. Then this vector is matrix is B double bar. Then this is delta U. Again, when I say delta U, it is all of the differential control signals, right? From start to end. Now you can use this equation and replace x tilde in the objective function, or cost function, this one still. So you substitute there. When you do that, you get this long equation. But again, it's just the label, right? There's nothing new over here. And then what you do is you have this x tilde transpose up to this point. This is x tilde transpose, and this is x tilde, right? You keep writing it. And here also you have x tilde. You substitute for that. And then this is the last term. And then you multiply this, expand this into 1, 2, and 3 terms. Okay, you only need to do this once. It appears in linear quadratic regulator. It appears in discrete time optimal control. It again appears in model predictive regulator, model predictive tracking control. Is the same process everywhere. Okay, then you expand this into 3 terms here. Then some similar terms, you add them together like that. You follow this sequence, and eventually uh, you get into this format: half delta U transpose B double bar transpose Q double bar B double bar plus R double bar delta U. So this is delta U and U combination. Okay, you can see it over here, delta U and U combination. This term, right? Uh, and rest you put it into this format. That is delta U and X. There's some combination. You can see it over here. Uh, delta U and X. Can you see that over here? This delta U and X, right? So you have to combine these terms together. Right. Take some time. Okay. Take some time to resolve these terms. Here you get 3 terms, 4, 5, and 6 terms altogether. Right. And in the 6 terms, you combine some of the terms together. And here you have 1 term, you have second and third terms, only 3 terms. Now, the one with delta U transpose and delta U, right, is very important. So we write like half delta U transpose H double bar delta U. Then the other 2 terms are combined together in this format, right? X0 transpose R transpose as a row vector here, and then the column as A double bar transpose Q double bar B double bar and minus T double bar V double bar, and that is F double bar transpose delta U. Okay. Now we see some similarity over here. The transferred system, right? Uh, we eventually get to the same format we had earlier. What is that? Half U or delta U, H double bar or H bar, delta U or U, right? So you just need to replace the terms. Earlier it was U, now it is delta U. Earlier it was H bar, now it is H double bar. Right here, you had F bar transpose U, now it is delta U. And before X double bar, you had X0, now it is X0 transpose R transpose, right? With this slight redefinition, you now made the same pattern here, this equation. Now the initial condition here is X0 and U minus 1, because you know delta U, when delta U is 0, it comes with UK minus 1, previous control signal plus the differential signal. So this is the new initial condition, and UK minus 1 means previous signal. So when you are moving the prediction horizon forward, right, this U minus 1 is the last signal of the previous horizon. Okay, you know that, except for the very first time horizon, the prediction window. There, you don't have anything in the past. Because now you're getting going. In that case, you can set it to 0. Okay, after that you know it. Then you differentiate J with respect to delta U this time. Earlier it was with respect to U. Okay, and this is the answer. From that you can find out the optimal differential control sequence, right? Remember, this is not for the entire plant. This is only within the prediction horizon. It's a very, very simple feature introduced into the standard algorithm. But this very simple technique uh, gave it a totally different name and open up a lot of applications. Okay, so now you have delta U transpose star, the optimal control sequence. Okay, so this is for 0, right? For any k, so for any k, anywhere within the control duration, you can calculate the optimal sequence this way. So you have x tilde k, rk plus 1 up to rk plus np minus 1. Right? You can have your references changing. You don't have to have fixed reference now. Right? You can have your k different. Even different reference signals can be used, but they are constant. Okay, they don't depend on any of the other variables. They are constant, but they are different, not the same thing. So that is why it is called tracking. Okay. So this is the model predictive tracking control algorithm. We start off with A, B, C, Q, R, N, and P, same as before, and you do this computation. All of these matrices should be computed offline, and then you enter the feedback loop, where you calculate X tilde, right, using the present state and the previous controls together, and you compute the optimal differential control sequence, right, using this equation, and then you calculate the actual control signal by adding u star delta u star to the previous control signal, that is u star k minus 1, and you apply that to the plant and update the state, and you get going like. Now, if you do the unconstrained model predictive tracking, applying this one without considering any bounds for the control signal, upper or lower, right? The ideal actuators. Uh, we'll see this exercise, Appendix M. Uh, Let me launch code from there. Appendix M, where is that? This one. There you are. Let me explain you the plant here. Uh, so this is basically the control duration. Okay. The point 2 is the sampling interval. This is the uh, total horizon, 40. Uh, Duration is number of steps times time sampling interval, right? The total time. This is the time duration for this window. Then what else? Can read through this one without much trouble. I want to bring you over here. Yes, AC. This is the plant system matrix. B is the dry matrix. A B C D. Right? Because in your algorithm, you need these ones to get going. For a particular plant, A, B, C, then Q and R are the cost for state, cost for the control, like that should be given, right? They are there. And then these are the other matrices, big ones. This is the R matrix, right? This is Q matrix. This QBB means Q double bar, right? This A double bar, like that. Okay, so study a little bit, and then you enter the control sequence. This is the model predictive tracking control, just four, 5 lines. So for this one, this is the result. You can see that it's a second order system. You have two state variables, x1 and x2. X1 is the continuous line over here, right? This is x1. X2 is the star line. This is the x2. You can see x2 increases when eventually goes to 0. Probably x2 is the rate of change of x1. So therefore, at this point, rate of change is 0. So therefore, this will maintain the level. Okay, right. You can see the reference is probably somewhere over here, 1.6 or something, right? Check that with the MATLAB code. And bubbles are actually control signals. This is a control signal that you can see this stepwise, right? This is the optimal control uh, signal, right? And the step is the delta. You can see the deltas, right? This is delta is what is optimized, but it is added to the previous control signal to get the actual control signal, and that is what is sent to the system for state change. And also, very importantly, you have this dotted line. That is the reference. You can see this reference over here. Eventually, it gets over here, but this is the reference before that. You can see x1, the actual output, follows the reference with a little time delay. Right? This is true tracking control, not regulation, tracking. So you have this actual curve and the reference very closely apart. Right? So now this is unconstrained. We don't have any constraint for the control signal. So therefore, this control signal, you start off nearly 0, but eventually it goes to very high level, 3 point something, and stay there. because you can't bring the control signal to zero like in other cases earlier when we were dealing with regulators. Now you have to maintain it at that point, but the delta U goes to zero, right? That's fine, but level is maintained because you want to maintain x1 at a non-zero level, higher value. You can't maintain it there, right, if you don't have this control signal in place. You have seen probably this one in PID controls also, right? When the system is settled, right, um, there's no error. So therefore, proportional controller is zero. It doesn't do anything. When there's no rate of change, the derivative control is also zero. It doesn't produce any control signal. But there is a big non-zero control signal produced by the integral controller. And that is what keeps the state at that reference level without letting it fall down to zero. Okay. So integral control is very important, therefore. Okay. Now let's go back to our notes and try to get the constraint model predictive tracking control. So this time is the same example, but we introduce code prog within the uh, optimal control loop, right? But you don't have to worry. It's done by MATLAB. Inside the model predictive tracking control, you include hot prop now, okay? Without you doing computation using the famous equation, right? H inverse F. But now you give this H inverse and F into quad prop with the constraints and ask MATLAB to derive delta U sequence for you, right? So it is appendix M 1032. What did I use? 1032, isn't it? Is there anything else like 1032? N. Man, probably N. So these codes are not very different to each other. You can see 80% the same, but there's a little addition on top of that. And I gave it a different name. Yeah, otherwise, even for a small change, you need to have a different name to keep the identity. So if I run this one, this has constraints in the model predictive controller. So let me check that inside the loop. Uh, there you are. You can see this one, code prog, right? So this time we are not actually multiplying HBB and RBB, right? But we give the upper bound and lower bound and together into the code prog command algorithm, which gives us the optimal differential control signals. And out of that, we pick up the first one. And the result is like this. You can see it. On the left is what we had earlier, right? On the right is what we are having right now with the constraints. Now, we have 2.5 as the limit of the actuator. You can't ask anything beyond 2.5. So when you go up to 2.5 over here, you have the identical result. Both left and right hand side, they are identical. Up to about, in time, roughly around 5, 5 seconds. Up to about 5th second, both are same. And at time 5 seconds, controller hits the limit 2.5, and after that this is the maximum level. The quad proc says you okay, you can't have anything more than that. So because of this saturation, we call it actuator saturation. Now what seems to be very good tracking up to about 5th second, now the two curves are falling apart, right? You can see the x1 actual value goes like that, and the reference is like that. There is a error generated there. Okay. All right. So this is very interesting.